Hi. Oh, hot mic. Hi. Thanks everyone for staying so late. I know everyone's excited to get home, and it's going to be a fun one if I can figure out how to do stuff. All right. Introduction to Online Machine Learning Algorithms with Trevor Grant, which is ironically at the end of the day after you've been hearing now about online machine learning algorithms and so on all day long. So, but I appreciate having the chance to come out here, and I won't gripe too much about the scheduling. A little overview of what we're going to talk about today. A little bit about me, what this talk is all about, and all the buzzwords, and really a lot of what it's going to be is disambiguation of buzzwords, because they're playing really fast and loose because it's a new thing. Streaming is new, machine learning is new, deep learning, and it's buzzword soup, and we're gonna square some of this stuff up. Actually, it's probably best that I went at the end of the day, because I've been sitting here watching like talks all day long. I'm like, ooh, I'm gonna be kind of sharp shooting them later, and that's all right. So, because it is what it is. I'm the king of the buzzword game. I love throwing buzzwords in things, and we're going to talk about basic online learners and some really intro and like how these things work and why they work, which I may go a little faster through because it's been an entire day and there's been like some really good coverage on a lot of this stuff. And finally, we are going to do what's some really fun thing. We're going to do GPU accelerated machine learning on a Flink streams with Lambda architecture and hybrid, more stuff. Sounds really exciting, right? We're going to build our own. It's not. And it's going to be kind of the punchline to this whole thing is, while all of this stuff sounds so cool and like, man, it's so far out there, it's like 20 lines of code. It is not hard to do this. This is comically easy. Everything will be available, slides, videos, GitHub repositories. So without further ado, let's get started. I'm Trevor Grant. I am an open source technical evangelist at IBM, which is a lot of fun. I get paid to go around and give talks and work on my favorite Apache projects. And if you're ever looking for a job and you have a chance to be an open source technical evangelist at IBM, I highly recommend you take it. It is just a great time if you like doing those sort of things. I'm also a PMC on the Apache Mahout project. And so you will be getting, how many people have heard of Apache Mahout? Hey everyone, so you're gonna get some Mahout in your life. I'm a blogger. I've got lots of fun blogs, and I will probably blog all about this later this week. And MS of Applied Math. I used to be a data scientist. It's not cool anymore, so I don't do it. I'm on Twitter, I'm on email, I have Apache mailing lists, so yeah, hit me up. All right. Why any of this matters? I think I already kind of got into this a little bit, but again, we're going to disambiguate a lot of the terms related to machine learning because they're getting thrown around a lot. Hopefully your key takeaways from this is you will no longer accidentally use words incorrectly. And then when you hear somebody else, you can be very pretentious about it and be like, actually, that's not an online algorithm. That's or don't. You can, and then the bonus material with our cool online recommenders. We're going to have a little bit of math, but it's not going to be too bad. I have seen worse. Weighted averaging and matrix times vector is about as deep as we're going to have to get with it. So I won't. It's the end of a long day. We've been getting hammered with a lot of really exciting stuff, and I'm not going to beat you up with difficult math at the end of the day. And there's pictures. There's two kinds of pictures in this presentation. There are illustrative graphs and animations to help you wrap your mind around complex points, and there's pictures of my pets, because apparently the spirit of the times is we throw lots of unrelated pictures into our presentations. It actually hasn't been that bad out here today. I thought about pulling all the animal pictures out, and I decided not to. So there they are. Buzzwords. A lot of buzzwords going on. Online, offline, Lambda, Kappa, statistical and adversarial models. Actually hasn't been talked about a lot today, so maybe there'll be some more. Real time, which is my favorite buzzword of the day. And so on. Online and offline models. This is the big thing. This is what we've been talking about, all this online. And the key point that I want to drive, if you take nothing away from this talk, online models are for every piece of information we get, we do something. That's it. Your Spark mini batching is not onlining unless your batch size is 1. It just can't do it. Anytime you see, oh, Spark mini batching, online models, it's not. I don't know that much about the new Spark stuff. Maybe and a lot of your Flink isn't either, unless you're doing, there's I think a very specific case. If you are doing a sliding window, and every time, it's like sliding window size 1, and every time you slide it, then you're doing something and you're updating and you're making some new action, that's an online model. But just because a model is not online doesn't mean it's useless. That's okay. Everyone wants to call their stuff online, 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 because it sounds cool. And it doesn't have to be. You can have perfectly good models that aren't online. Online doesn't necessarily mean it's low latency. Just because you're doing something every time you get a record in doesn't mean you're doing something fast. Get a record in and train a whole new neural network on it. That's not quick, but it's online. Offline isn't necessarily high latency, but it is batches. Anything that's not online is offline. So definitions according to Trevor, you can quote me. Let's see. Yeah, so the slow online, the fast offline. An online model that would be very slow. Imagine there is a stockbroker who doesn't pay for a lot of good access to his market data, so he has a Python job that at the end of the day, as soon as the end of the day results for the stock market post, it goes and hits his Python job, and he goes and does a bunch of stuff, and he fires market orders back. That's online. It's once a day online job. It's barely even streaming, but it's online. You have a high frequency traders with their algorithms burned into silicon, and every 15 milliseconds they're batching their jobs and doing something. That's offline, and that's some crazy razor's edge fast offline. The key point being, don't get caught up by the buzzword. Just because it's online doesn't mean it's exciting or useful. Well, it could be useful. They're both useful things, but Lambda and Kappa, in the context of machine learning, this is another, we've been talking about Lambda and Kappa today. A Lambda model is what we call it anytime we train our stuff offline. We train ourselves in like batch, using some other thing, and then we feed the job to our stream processor like Flink to do its thing. A Kappa machine learning model, every time we get new information, we change the model. So I want to kind of dig into this a little more. Lambda model, we're doing all our training, we're doing our Spark. This is most of what we've been talking about today. And you're giving the model to the stream processor like Flink to do the scoring. So it's got the model loaded up and it says it makes predictions, but all that training has happened before. And on a Kappa model, every time something comes in, we're changing the parameters of the model, we're updating the parameter space, or, and this is really where it gets a lot more useful, let's say we can change the structure of the model itself. We've got a new variable. If we're doing language processing, we've added new words. Our TDIF, our TF-DFIF has gotten bigger. We've changed things fundamentally. So that's the difference between our Kappa and our Lambdas. Lambdas can't handle Novell information. They can't handle changes in structure. They can't handle, to Joe's point at the end of Dean's talk, the side inputs. They can't handle just totally changing models. Because a trained model, when we do these traditional, like our linear regressions, our clustering, they were trained on a certain structure of data. And so the information when they predict on it needs to be at the same structure. Okay, I think I'm beating a horse at this point. Yeah, vectors changes. Okay, statistical versus adversarial models. How many people have heard of adversarial learning models? A couple. Statistical models are all the models you've heard of. The stochastic gradient descent, k-means, linear regression, blah, 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 blah. We train those with our mean squared error, with our area under curve, with our confusion matrices. Adversarial models are like spam filters, fraud detections. They are model versus environment. They are somewhat more difficult to train because the environment gets smarter as time goes on. You set up a spam filter, spammers come up with a way to beat your spam filter because they know how the rules work. Same with fraudsters, same with hackers, etc. A/B testing, you need to have models that get smarter over time. A fascinating field, and this is Introduction to Streaming Models, so check it out. Real time, my favorite buzzword, doesn't mean anything. If you have something you're talking about and you want to make it sound exciting, call it real time, because it's whatever. I've worked at companies where the industry standard was something took 3 weeks latency, and they could do it in a week. It was real time. I worked at another company where people met to talk about data that was 3 days old and make like manual optimizations about it in like a meeting. Real time. I worked at Jimmy John's. So I define real time as significantly faster than you would expect otherwise. Jimmy John's has real-time sandwich delivery. So yeah, that's your safe fallback word. If you're not really sure where your algorithm and your machine or whatever it falls into, it's real time. Basic online learners. If you're, okay, yeah. K-means, this is how K-means works in a picture. You've got a bunch of data. There is a mean that tries to like say, okay, all this data is close to this and the means move around in the space. If you know K-means, this is the gist of it. Yeah, that's how clustering works. But in this, you have the full data set, is the idea. You got a full data set, you throw a few random points out there, you say, okay, I'm gonna have 4 different clusters, throw 4 points out, and you find a model that makes sense that these are the buckets to put things into. If you were doing online K-means, the why some algorithms go online and some don't, the way this is gonna work is you get a new point, you say, all right, it's closest to the red one, so we'll call it red, and then the middle of the red point kind of moves. That's how online learning works. It's not super exciting. It's pretty easy. It's easier than most of the math that goes into it. In a similar way, linear regression. We got a bunch of points. We kind of just keep guessing a line until we find one that fits it the best. If you were doing that online, you've got a line already. You got a new point. That's the new line that's between the last line. This isn't exactly right, but it's illustrative. All right, let's just bump our line a little bit. That's how online linear regression works. Sounds super exciting and all this stuff. It's not. You can also do this with, I did 2 examples. That's our second iteration. Deep learning works the same. It's a little bit more to back propagate a neural network. Online, you're just doing it one step at a time. Why would you do these traditional methods? So here's another problem. It's when we start moving at fast-moving data coming in, we kind of got to turn a lot of our things that we think about and why we're doing machine learning in the first place goes on its side. Machine learning, usually, we're doing some flavor of we want to describe the data set. It's descriptive statistics, and they might be, we want a neural network to describe, or we want some sort of predictive value. When we're doing a stream, we're not seeing the whole data set, so we can describe the stream, but it's what's our goal? What's our angle? What are we trying to get out of it? And usually, right now, when you're using those traditional methods, it ends up being anomaly detection. And anomaly detection makes sense because we say, all right, we have this model, be it a cluster or linear regression or whatever the case is. We have described the world as we've seen it. We know what normal looks like. And if this is a significant deviation from normal, sound the alarm. But that's not to say that's only because that's the only reason we can. It just is the thing that kind of jumps out. It's it's the low-hanging fruit of all of this. Nope. And so yeah, that gets into challenges and solutions of things that we're doing with online learning. When you've got data coming in, normally when you're doing like a full data set, you are training it because you know what the answer is. You've gone long enough and you said, okay, these things and it's this. But when you're looking at unemployment data coming in and all these things, well, we won't know for another 4 months what the real unemployment rate is. So how do you train that model in real time? This raises some things. It's not unsurmountable, but it's also, you can't say, oh, well, you just always do this. I don't know, man, it depends. Are you willing to wrap your mind? And that's what a lot of these other talks have been in. But these are problems we have to think about. You've got the same problems that you normally have with your regular algorithms. If you're trying to train a neural network and you only have so much hardware, the thing's going to topple over. You're going to have back pressure. So now we have not only the standard problems of regular statistics and all the problems of regular streaming algorithms, but we also have the problems of we don't even know the real right answer to train on, and we might not know it for a long, long time, like months. If you know it in a couple, maybe it's going to be a minute later. Okay, maybe you're training in real time and there's some sort of lag. It all, again, context is dependent. Adversarial analysis. If you were in for the TED Talk, this is there's 2 ways you can do this to grade your online algorithm. You either take the offline version, and we expect that the offline version that had the entire data set to train on is going to do a better job than the one that's like only getting in for like on a streaming version. Another way to do this is the canary idea is the same idea that you have. Okay, how are these things doing next to each other? And the idea is because the world is changing, your algorithm, it's not just a question of how is it doing, but when is it broken? If you, I've been in trading, there's a lot of, you get like a trading strategy that's in play and it's working and it's working and it's working and it's working until it makes you money, until it doesn't. And so then the question is, when is that thing going to blow up and how do you get out? Things have corrections and things have hiccups, or are you just about to get wiped out for the last 11 months of your trading strategy in one foul swoop because you didn't pull the plug fast enough? And so it's a kind of the same thing. Really, you can learn a lot about the general theoretical problems of online algorithms and machine learning by going back and reading trading books from the late 80s and early 90s, because these are all the same problems. These guys have been dealing with information coming in one-off with latency because it took time to get there. It's a fascinating study. So the A/B tests are really, in my opinion, the best thing you can do. You've got these things running live. You got 2 of them going. You got 3, 4, 5, 6. Who's doing the best? Who's toppling over? You've got learning rates, other knobs. You could have the same algorithm. You've turned some knobs, but it's always a question of like recommenders. And again, going back to Dunning's talk, because things happen, you can never go back and say, what if I'd have done this? Because you are interacting with the environment that you're playing in, and when you do things, you've changed history because your algorithm made an action, and you don't know what would have happened. So A/B tests are my recommended way to go. Lambda recommender. How am I doing on time? Whatever. It's going to be done when it's done. Lambda recommender. All right. This is how we do our cool online thing that everyone's talking about in like just a handful of lines of code. How many people are familiar with recommenders in Java? Am I mainly talking to data science in here? Ish? No? Okay, well, thanks for at least raising that. I appreciate someone raising their hand. Correlated co-occurrence is a lot easier to keep track of than alternating least squares. It doesn't require matrix factorization, and it is multimodal. I am not going to dig too deep into this because I said I wasn't going to go crazy on the math. Here's the gist of a simple co-occurrence matrix or co-occurrence recommender. You have a history of action. Like imagine a matrix that's like users, actions. Take that matrix transpose. You have a co-occurrence matrix. You take the log likelihood. Because it normalizes everything out. You've got a history of the user's vector, and kaboom, recommendations. Either the math is very intuitive or it's not. Look into it later. I don't know. We can expand this out into a co-occurrence if you have multiple actions. The key here that the math will make sense is every matrix has to have the same number of rows. So you've got to have the same users. You keyed on the same users, for example. It doesn't have to be users, but you've got to have the row space the same across the way. And because you've done that log likelihood, it's normalized everything. so that you can add everything back up and there's some sort of sanity and it makes sense. And you have the history of each user's thing. This is a very nice tag. Note how many logos are on this page. That's how you know this is a very impressive thing that I've done. I will sidebar here for a moment and do my momentary pitch for IBM. Oh no. Nope. There it is. Nope. Oh, this is bad. All right. My momentary IBM pitch. This is all available in GitHub. And if you're going to do it, it really does make sense. IBM sells Twitter data, and you can sign up and get a 30-day free trial and get a lot of access. And so if you're going to build this recommender, you want to have a huge corpus of historical tweets, log in, there's a Python script, you download it all, you get your whole thing, you can do a query. In this case, we queried, I think I got 50 or 100,000 tweets about pizza, because that makes sense. It's an important thing that we want to recommend things about. Twitter is a really, really fun thing, especially for working within Flink, because it's a thing that's always streaming data and you can do weird stuff with it. So we download all of our historical tweets about pizza. I like the, we get lots of pictures of all these logos. So we load all our historical tweets into Spark. We use the Mahout library, which runs on top of Spark or on top of Flink. It does the calculations of all those AT times B, and then we pass all those matrices up to Flink, who then starts a streaming job, just plugged straight into Twitter, and then uses the Mahout again and generates our recommendations. This is a very silly example. I take tweets and recommend hashtags for no reason at all, but there it is. I realized I could have done probably some really interesting and cool things, but I didn't, and I leave it as an exercise to the user. So I've got a Python script that takes all these historical tweets. This is more or less what our input matrix looks like. It's user IDs and hashtags. It does another one. It's user IDs and the words that the user used. There's about 3 or 4 things like this. And here's some Spark code. And it's a Flink talk, so I'm not going to go too nuts on the Spark, but the gist of it is we load it up, we turn it into these mate things, and then this line right here does all that matrix transpose times matrix and spits them all back out. I save those to a disk. Oh, back to the math. That's the part I just calculated. I save it to a disk. This is just the mapping part of my Flink job. How many people have programmed a Flink job before? Oh wow, it was much better than most of their talks. I got the good ones in here. So this is the part. It's a mapping job. I got my stream source. I'm mapping it out. I've loaded my matrices. I take my tweet. I parse it out. Take the matrices. This line does all of this. Go back. Saying again, this line. It's all R-like syntax, %*%. And we've got recommendations. There is some more code that does some pretty printing. And these are some examples. There's some text. There's some recommended hashtags. I'm going to be very candid with you. This whole algorithm, because I was very lazy, and like when you're doing natural language processing, some basic things you do. You strip out the stop words. That's a good start, stripping out. I didn't bother doing any of that. So this is very garbage in and very garbage out. So I looked through it and I'm like, oh, this one looks like it was a real result. So does this one. I think the whole thing will work. It seems sound. You just need to do a little bit of doctoring on it, but it does. So we've got an online Lambda recommender. Buzzword Soup. We've got an online hybrid Lambda recommender using Spark. It's GPU accelerated. Online recommendations, cognitive AI. Sounds like a cool talk, yeah? It's not, it's like 20 lines. Don't let people overhype you. Oh yeah, this is also GPU, shameless Mahout plug. This is all with a change in dependency, GPU accelerated. GPU accelerated machine learning on Apache Flink, yeah. You also wouldn't probably do this in real life. As many people have talked about, you would store all these in like an Elasticsearch and it would be as a service and blah, blah, blah. But it's whatever. It was very demonstrative. Conclusions. I'm going to try to land this plane. You guys ask me easy questions and not make me look like a dummy, and then everyone buys me beer, which I think it's not even for sale, so easy. A lot of buzzwords flying around that we've covered. The point being is, you can do one of two things. Don't get caught up when you hear people when you start hearing people throwing all these buzzwords at you and like rapid fire, they're like, they might not know what they're talking about. Maybe they're just trying to sound impressive because these things don't really mean anything. Or you could be evil with it. And when you're trying to sell your open source project or venture capital idea or startup or whatever, you'd be like, yeah, real time, GPU accelerated, streaming, machine learning, and know how to do it in just such a way so if someone catches you, you weren't really lying. So I hope that's what you got out of it. And questions. How am I on time? Do I need to talk more? I don't know. I'll just do long questions.
Questions?
6:18. I should have planted some. Yes.
You said you recommend doing A/B testing for models that are not performing very well anymore. Can you tell us a little bit more about that?
The A/B testing on models that have been up for really then it's hard to measure any kind of performance on this because you're interacting with your environment. So I would always say, even if you've only got one model and it's your first one out of the gate, send it out and then send its cousin out with a slightly tuned knob, or so it's ever so slightly different, and you can see, okay, one's doing better and one's doing worse. You want to have some sort of baseline, and it makes more sense to have another baseline model, or at least let the other model that's being considered, as Ted was saying too, run off of fresh data. Because the only way you can compare this is, to look at and he even laid out some problems that even when you do that, there's problems you can get into. But always do A/B testing. It's not a question of, I guess, the model being a bad model. It's, you'll never know, and you can't fairly judge it unless you have something to hold up next to it. Which is not saying anything at all, but it is what it is. Okay. Yes.
Went back to the CCO example. So when you're actually trying to explain that online recommendation, you can actually do online learning on that as well, right? So we can just have a delta on that matrix and that's it.
You 100% can. Yes. There is an active, are you currently following the Mahout mailing lists?
Not really.
Oh, well, because there's an active thread talking about that. Not to love on Ted Dunning too much. His idea from a mailing list post exchange back in 2014, but there has been a revival of it. And yes, this could be online and the only thing you have to do is these little matrices through here, every time you get a new record, you just update those matrices. That's not exactly trivial. It would, I think, you'd really have to think okay, I've got a new record. Now I've got to kind of work it through all this multiplication. But at that point, you can start, you've got new words. You can pop on new hashtags as they show up. You can pop on. And when the thing shows up, maybe it's not super useful. It's, it's going to take some burn-in time. But you're saying because whatever it is you're doing, that's okay. As it stands, yes, you would have to recalculate. But yeah.
I guess my point is you don't need to store any historical information about what past word you've been seeing. You only need to train on top of whatever that specific one record. That goes back to your online definition.
Yes.
To have a reaction on that specific
yes.
one.
Yes. So this is, all right, and to push this example a little further, this is online recommendations. It is offline training. So yeah. But yes, to make the training part online, that's what you would do. Yes. As it stands in the current code, if there's ever words or hashtags that have not been seen, it just kind of throws them out. Which is, again, it's not a great example, but it works.
James?
Okay. Well, if there aren't, somebody get out a camera and take a picture as if I was doing. Oh wait, no, that's right. They got all my pictures of the exciting logo chart. All right, I'm very vain. That's important to me. And now everyone knows it. And for those watching at home, I may have said a lot of things that people don't agree with. Please feel free to troll the YouTube comments, and I will flame war you right back. All right.